자, 오늘은 챕터 4의 마지막 부분 하겠습니다. Fourier Transform의 Continuous Time Domain에서 Fourier Transform을 하는데 중간고사까지 여러분 열심히 공부했죠. 이제 마지막 부분 Modulation Property만 하면 이제 끝나도록 하겠습니다. 오늘 부득이 우리 어머님이 수술을 하셔서 오늘 부득이 동영상으로 강의를 진행하는 걸 양해해 주시고요. Okay, before doing that, let's cover some Fourier transform that will be used during this class. So, especially let's do that for periodic signal. So we know that any periodic signal can be represented by xt of k minus infinity to infinity ak e j omega k 0t as a combination of harmonically related functions. Now, if I want to represent xt as 1 by 2 pi x j omega e j omega 0, not omega 0, just omega t d omega, then we want to find some match between ak and xj omega. This is Fourier series and this is Fourier transform. Okay, then we want to multiply 2 pi. So this is 2 pi. They will drop out. And I want to select just a k, specific k. So we use impulse, right? Sigma k equal to minus infinity to infinity impulse for specific k. So omega minus omega 0 k and multiplying a k. So just reminding that x j omega for periodic signal is minus infinity to infinity ak 2 pi delta omega 0 minus omega 0 k. Okay, this is just reminding. So using this, let's find the Fourier transform for 3 signals. For example, xt equal to 1. What's the Fourier series? Periodic signal, right? Periodic signal with any period t. So, its Fourier series is simply 1 with a0 equal to 1 and all other a's are nothing. So, its Fourier transform is simply 2 pi 1 delta omega minus omega 0 where omega 0 k with k equal to omega 0 k with k equal to nothing. So 2 pi delta omega. This is Fourier transform for this simple constant. Next, what if we do e j omega 0 t? Then this is simply Fourier series with a1 because omega 0 k equal to 1, so a1 equal to 1 and all other a's are nothing. Therefore, xj omega is 2 pi delta omega 0 minus omega 0 k with k equal to 1 and it's ak equal to 1. So 2 pi delta omega minus omega nothing. Or we may do that for cosine omega 0 t using the Euler identity. Simply we can write it as e j omega 0 t minus e j plus e minus j omega 0 t. So here, this corresponding to a equal to 1, this equal to a1 equal to 1, a minus 1 equal to 1. So it's simply half 2 pi delta omega minus omega 0. Here, 2 pi delta omega plus omega 0. So 2 will drop. So we get simply this result. Okay. Similarly, you might be able to get sine omega 0 t, which is turned out to be pi by j delta omega minus omega 0 minus delta omega plus omega 0. Okay, so this is simple review of sum of Fourier transform. Now let's go to the final topic. It's multiplication property. It means multiplication of time signal. RT is multiplication of two different time signals. And you may guess that it's convolution, right? If I do the Fourier transform, it's kind of convolution form. So R j omega is equal to convolution of two signals. 1 by 2 pi s, its convolution, this p j omega. So writing them down in a convolution form gives convolution minus infinity to infinity given omega. So p j given omega minus any arbitrary thing, for example tau or whatever, and here we select theta, so theta, theta. So this is convolution form, right? For given omega, or in time domain given t, tau, t minus tau, d tau. Okay, it's convolution. So this convolution can be used in various manner. We will see two examples. One is sinusoidal amplitude modulation, and the other one is frequency selective filter. So first thing is sinusoidal amplitude modulation. In the figure of the lecture note, we see some specific Sj omega. It has a specific form, let's say this with amplitude A and bandwidth to omega 1 to minus omega 1. And let's select one filter, P, as cosine. If Pt is cosine omega 0 t, we know that Pj omega is pi delta omega minus omega 0 plus pi delta omega plus omega 0. This is any signal. This is sinusoidal function, sinusoidal form. If I multiply St and Pt in time domain, it's convolution of Sj omega and Pj omega. And Pj omega is, here the amplitude is pi, and this is delayed by omega 0, and this is advanced by minus omega 0. If omega 0 is positive, then this is this form. Then the resulting signal, if we think about RT as ST times PT, then by this multiplication property, it's convolution of two signals. So it will turn out to be a specific form. Shall we calculate it? Okay, let's calculate it. This is actually the next page, example 4.21. So if RT is given in this form, then Rj omega is convolution of 1 by 2 pi convolution of Sj omega Pj omega. Now Pj omega is given in this form, so pi drops, so half S J omega convolution. Okay, let's write delta first. It's commutative, so delta omega minus omega nothing convolution Sj omega plus delta omega plus omega nothing convolution Sj omega. Then, by the definition of convolution, we can simply write down minus infinity to infinity. Let's write theta minus omega nothing times Sj given omega and minus theta d theta. Okay, the first topic. And the second topic is given omega. So this is tau t minus tau. Tau t minus tau. So tau, instead of tau, I write theta Sj t minus theta. Okay. Then this is valid when theta equal to omega nothing. This is valid when theta equal to minus omega nothing. And if delta is integrated, then it's equal to 1. So finally we have half S omega minus omega nothing J plus Sj omega plus omega nothing. Then what happened? What happened is that original Sj omega is shifted by omega nothing and scaled by half. So original this form is shifted by omega nothing and scaled by half. So it will have this form. And here it's advanced by omega nothing and scaled by half. So what we see here, given any original, any arbitrary signal, for example my voice or whatever, if I multiply sinusoidal function, however, the original form is conserved. Just amplitude is different and frequency is a little bit different, but original information is conserved in this multiplicated signals. So we use this communication. We send this signal to the base station. So this is your voice and it's multiplied to sinusoidal function, and the result is conveyed to the base function. Then the next thing is to recover the original signal from this received information. That's the next example. Let me write it. Let me draw the next example here. So next example is to recovering. What I receive is, let's say, rj omega. This is what I received. The same with that one. Minus omega 0 and omega 0. And this is 1/2. Okay, I received it. Then I need to recover the original signal. To recover the original signal, we again multiply the same signal, pj omega. Again multiplying the sinusoidal signal. So pj omega is omega nothing minus omega nothing, and it's pi. Then if we do the convolution of those two things, let's see what happened. Okay, let's say gj omega is their convolution. Let's calculate it. Then, example 4.22 is GT, I'm sorry. Given GT is multiplication of RT times multiplication PT for the same PT. Then what will be GT? Here RT is Fourier transform, PT is Fourier transform, and what will be GT's Fourier transform? That's the question. Then we know that Rj omega is given here. Rj omega is, oh, I erased it. Anyway, it's half Sj omega minus omega 0 plus Sj omega plus omega 0. Okay, this is what I received here. And I multiply cosine function. So cosine functions pj omega is pi delta omega minus omega nothing plus pi delta omega plus omega nothing. Okay, from the previous example, we know that if I do the convolution from the previous example, just what we did 4.21, we know that if I multiply given any rj omega with this pj omega, we know that rj omega will be scaled by half, and instead of s, I may write r, right? In the previous example, we did Sj omega and Pj omega. So whatever S form, the result would be like this. So instead of S, let's think about R, because S and R is arbitrary. Then I may put R here. This is the just direct result from the previous example. Then instead of omega 0, let's put it here. Omega 0 and omega 0. Then it's half Sj omega minus omega 0 minus omega 0. So omega minus 2 omega 0 plus Sj omega minus omega 0 plus omega 0. So this is omega. Next time, I put this here and here. That will give Sj omega plus omega 0 minus omega 0. So omega plus Sj omega plus omega 0 plus omega 0, omega 2 plus 2 omega 0. So finally, half Sj omega minus 2 omega 0 plus, there was a mistake. It should be 4, I'm sorry. It should be 2. Here it should be 4. Yeah, here it should be 4 because I did convolution. You may check it by following one by one manner. Here it should be 4. Yeah, right. Should be 4 because r has half factor. So that half factor is multiplied. So it should be 1 by 4. Okay. And this is 2s. So it's half Sj omega plus 1 by 4 Sj omega plus 2 omega nothing. Okay. Then, if I draw it, it's half. So, it's A, then it's half A. Half A. And there's original signal. And this shifted by 2 omega 0, and it's 1 by 4th. So, it's a little bit smaller. And shifted by 2 omega 0. And similarly, minus 2 omega 0. Okay, will look like this. Then, what will happen if I put ideal low-pass filter? To this G. Then, we will recover the original Sj omega, only scaled by half. So I just multiply 2 and I can recover original signal. So that means if this is my voice, I'm using my cell phone, and this is modulated in this way by sinusoidal function, and it's transmitted to, it's broadcasted, then in the base station, if they receive it, or another cell phone, if they receive it, they multiply again the sinusoidal function, and then if they use an ideal low-pass filter, they might be able to recover the original signal. So this is basic building block of communication, and actually it's on chapter 8, but we are not going to cover it. But in the next semester, in the communication theory, you will learn the details how it works. So this is the first example of modulation property, that if RT is multiplication of ST, whatever PT, let's say, then its Fourier transform Rj omega is 1 by half convolution of Sj omega and Pj omega. Okay. And there's another application that is frequency selective filtering. Let's go to frequency selective filtering. Second example. Okay, sometimes you want to make some frequency filter that's just having specific bandwidth. For example, if this is frequency, you know that for given yj omega equal to hj omega, xj omega, this is input system, input to the system, this is output. So this works as a filter, right? This is frequency filter, frequency selective filter. And sometimes, for given specific omega c, you want to filter just this bandwidth, for example, let's say 2 omega nothing. And sometimes you want to shift it as you wish, move it like this. For example, if you just rotate the resistance, then filter is changing like this. You want to design that kind of specific filter. And using this property, we can design it if we have ideal low-pass filter in the way that I will draw a diagram after erasing it. Okay, xt is exerted to the system. Then, similar to the previous example, I multiply a sinusoidal signal, j omega ct, with specific center. C indicates center that I want to filter. And this is yt. And I pass through ideal low-pass filter. Ideal low-pass filter. So I put hj omega in a way that have a bandwidth to omega 0 to minus omega nothing. Then its output is omega t. Here I multiply again the same signal with minus sign, omega c. Center frequency. Then I get my final output, ft. And let's see what happened here for any given signal. Then we may assume that any given signal in this kind of form. Okay, x j omega, let's say this is this kind of form relative to omega. And if this is multiplied, if that is multiplied, what is this Fourier transform? This Fourier transform is simply two pi delta omega minus omega c. Then what will be yj omega? Yj omega is 1 by 2 pi. This convolution, this xj omega. Okay, this is yj omega. Then 2 pi will drop, and I do the convolution from minus infinity to infinity. Delta theta minus omega c xj omega minus theta omega minus theta d theta. Okay, this is convolution, and this is only valid when theta equal to omega c. So given y, it's given to be xj omega minus omega c. So y is simply shifted signal by omega c. It's shifted by omega c. So if I draw y j omega, it's shifted by omega c. Oops. Too much shift. Let's say omega c is here. Okay, shifted by omega c. Then if we pass through a filter, ideal low pass filter like this is hj omega, and what remains is w omega j will be shown like this. Then this w omega j is multiplied by, again, this. As you have seen, this is simply scaling, right? Scaling. So if you calculate, it will scale back to back to here, back to original position. So if you calculate it, you can easily see that fj omega is, here's minus omega c, and it will look like this. This is minus omega c plus omega 0. It's this omega 0. And this is minus omega c minus omega 0. It doesn't appear in the in the camera. Okay, so finally, what we have here is exactly, I cut this part. The center point was omega c, that's multiplied on here, and back inverse multiplied on here. And the bandwidth is 2 omega nothing. That's the same to this low pass filter's bandwidth. So I implemented this kind of frequency selective low pass filter. So if I change omega c on here, then I may shift it, right? Shift it through the frequency. So we implemented frequency selective low pass filter given the ideal low pass filter. So this is another application of this multiplication property. Okay, so we are basically done with all topics of chapter 4. One remaining, but this is so simple and straightforward, so I will mention it briefly here. That systems characterized by linear constant coefficient differential equation. System with linear constant differential equation. So we know that this is, if it's fully relaxed, then this is linear time invariant system, and its very general form is output and input. Output is ak, some linear coefficient, and it's differentiated by k times. Okay, differentiated by k times and have n differentiation. And here its input also can be differentiated by m times bk dk xt dtk. Okay, this is kind of a general form of linear constant. Linear differential equation with constant coefficient. Then if I do the Fourier transform for here, so I just do the Fourier transform here, and I do the Fourier transform here, because of the linear property, this coefficient will come out of the Fourier transform. And this differentiation, we know that if original signal is differentiated, then its Fourier transform is just multiplication of j omega, right? So we know this property, d xt dt, if it's Fourier transformed, it is j omega x j omega. So I multiply just j omega. Then if it's multiplied differentiated k times, then I just put k here. That's it. So for this I may write it as 0 to n, ak come to the front, or it may come inside, and j omega is done by k times, and remaining is yj omega. Similarly, bk j omega k xj omega. So from here we can find yj omega as this form, hj omega xj omega, what we say transfer function. And it will be simply given by this, nothing to m bk j omega k divided by n ak j omega k x j omega. Okay, this is transfer function for any linear constant differential equation. Okay, so this is the end of chapter 4. So we are done with continuous time Fourier transform. And from the next class that will be done on this coming Thursday, we will do discrete time Fourier transform. And as it is noticed, the next class will begin 2:10 because there's some kind of simulation of fire alarm. So it will be very noisy from 2 to 2:10. So we'll start the lecture from 2:10. Okay, that's it. Thank you for your attention.